Nice, how cool. Okay. Let's get, yes, manatees, the beloved sea cow. Okay, perfect. Okay. Let's see. Yep. All right. Okay. Grab the door here. Okay, so last time, so we finished a lot of the ideas in section 3.7. We were talking about rates of change, and we went through a pretty simple example, hopefully, that was easy to understand how the graph would relate to the story behind it. And then we talked about, throwing a rock up in the air and stuff like that. Went through and talked about how each one of these graphs are related, the position function, the velocity function, and the acceleration. Talked about how you could tell when things are speeding up, slowing down. And then we did a more difficult, kind of more abstract, where we just had a particle moving along a line. Again, we call that rectilinear motion, rectangular motion on the rectangular plane, stuff like that. We're just talking about a particle moving back and forth along the line, and we drew a diagram for what that motion would look like. And then we actually went through and graphed the position function, the velocity function, and the acceleration, and talked about each one of those things. When's it slowing down? When's it speeding up? When is it stopped? What's its position when it's stopped, and all that sort of stuff. Okay. And if we go to the last page, those motion examples are pretty classic. We use those all the time. But it's also important to see that you can actually use rates of change in lots of different areas. Might be business, might be biology, or something like that. So I've got a couple of examples right here. Pardon me. This one is from biology, and it says the population of manatees. And if you haven't seen the manatees, they're pretty darn cool. They hang around in Florida, usually around the wastewater that comes out of like nuclear plants and stuff like that. They like the warm water and stuff like that. They're actually pretty darn cool. So the population can be modeled by this function right here, where t is the number of years since 1990, and it says find the rate of change for the manatee population and give the units. So what we're interested in is not only what the population is, that would be important from a biology standpoint, but it would also be important to know, is that population increasing? What is its rate of change? So if we're seeing a healthy increase in the population, that would be good. If we see it level off to some extent, maybe there's something that the biologist would need to be concerned about. And definitely if the rate of change was negative, okay, we'd want to be aware of something like that. So essentially on something like this, if we have a function that represents that population, if we find the derivative of that function, that's going to give us the rate of change. And think about it, if we were to graph this, this is going to be the time in years here, and this is going to be the manatee population, so the number of manatees. So even from that, we'll come back to this diagram in just a second, you can figure out what the units on this would be. Okay, and maybe you can think about it without even looking at a graph or something. But we're asking here for m prime of t, and in order to find m prime of t, we've got to find the derivative. Now, what rule do you want to use on that? Quotient. Okay, so let's do the quotient rule. So that's going to be the bottom. So 1 plus e to the negative 0.2t. It's a comma. It's a comma. I should be a little more careful with that. That would be pretty wild if it was a prime, though. Okay, so bottom times the derivative of the top minus the top times the derivative of the bottom. And the derivative of the bottom is, we've got a 1, so that's a 0. And then we've got the e to the negative 0.2t. So that's going to be negative 0.2 e to the negative 0.2 t all over the bottom squared. So this is going to be 1 plus e to the negative 0.2 t. Close the parentheses and square that. Bottom, derivative of the top, minus top. Whoops, that should be a 2200, shouldn't it? 2200 minus the top times the derivative of the bottom, e to the kt. So that's derivative would be ke to the kt. And then all over the entire bottom. No real calculus there. We're just squaring the bottom, right? Okay. Any questions? Okay. From here on out, it's just a question of how do you want to write this? How do you want to simplify this? So that's going to be a 0. And luckily what I have here is just a big multiplication problem. So I've got a positive. Well, let's see. What is 2200 divided by 0.2? That does go in evenly, doesn't it? 400 something? 440. So this is going to be 440, and then e to the negative 0.2t, all over 1 plus e to the negative 0.2t, quantity squared. Yeah. Yep. The two negatives there. Everybody got it? So really not too terribly difficult to get this. And if we asked a question, hey, tell me what m prime of 1 is, okay, what would that represent? The slope when? At 1, at year 1, which would represent what year? 1990. In other words, it would represent the better word here rather than slope would be, it would represent the rate of change for the manatee population in the year 1991. Okay? What would the units be on this? Yep, it's manatees per year. Now, let's go ahead and figure out what m prime of 1, yeah. It's just, this is just manatees, number of manatees. It's just the population, okay? It gives the population with respect to time, so it's going to, maybe we have points that look something like this, okay? So it's just manatees. If we find the rate of change here, this would be manatees for the rise on the slope, and then this would be years for the run, so we'd have manatees per year. Okay, that's where our rate is introduced. Good question. Anything else? You're right. Okay. All right. So if somebody would plug this into the calculator, okay, and just tell us what number it is, okay, maybe it makes sense, maybe it doesn't, okay, but I want you to look at the derivative, okay. So for the people that aren't plugging this into their calculator, look at the derivative right here. And because of the specific functions that are involved in that derivative, you should be able to look at it and tell something about the rate of change we expect to come out of the calculator. One. Okay, so one suggestion is the numerator is exponential decay, so he's expecting something that the larger number we plug in, the smaller answer we get out. I'll take that for a couple of reasons. If we plug a number in, we do get, the numerator gets smaller, and the denominator isn't going to get any smaller than 1. Okay, so this is going to be, this function, this derivative is going to be a decreasing function. Okay. Can you tell me something else about it? Look at the bottom. It's the entire bottom squared. What type of answers are we going to get out of there? Positive. The bottom's going to be positive. What can you tell me about the top? $440 times exponential base e. Exponentials are always positive. Parent graphs for exponentials, as long as we haven't slid them up, down, or something like that. Okay. So this is a positive quantity times a positive quantity. This answer, this derivative, this rate of change is always positive. Might be a big number sometimes, might be a small number sometimes, but it is always positive. Okay. If this truly does represent the manatee population, why would that make me feel good as a biologist? They're always growing. Okay. The manatee population would always be going up. Maybe up just slightly, but it's going to go up. If that truly does represent it, and rarely do we find a mathematical model that will represent a population forever, but if this did, the manatee population would never go down. It would always go up. Okay? Now, usually these are represented by what we call logistic growth functions. So we're going to start off with a population. It's going to increase. And then realistically, it's not going to continue increasing. It's going to get to a point where it kind of levels off. It's going to reach the carrying capacity of the environment. Okay? So that's a logistic growth function. Okay? But notice the slopes. Slopes are all positive. Notice what Juan said. The bigger number you plug in, what happens to the slope? The smaller it gets. Okay? So good observations there. Any questions on that one? Okay. Who figured out what is m prime of 1? What is it, Ben? Manatees per year. Okay. So let's say we're right here. We're going to experience a pretty high growth rate. And then what happens when we get 10,000 manatees? That growth rate will start to decline, okay? Depending on what the carrying capacity of the environment is, okay? Too many manatees, not enough food, okay? Some of them would die a little bit, but the population would still continue to grow just slightly until we reach whatever the carrying capacity was, okay? And then it would just pretty much level off. It would grow asymptotically, is what we say. Okay, any questions there? Okay, sure? Okay, so let's take a look at the last example here. Okay, this is an example from economics or from business, and just a couple of definitions. So it says average and marginal cost, and it says if the cost function of producing a particular item, whatever it happens to be, if the cost function is C of X, and that gives the cost of producing the first X items in a manufacturing process, then the average cost, and the thing that we use here is we put a little bar over the function, and if you ever see a bar, it usually means average, okay? So we'd say C bar is given by, well, how would you find the average of producing X things? If it was 10 things, you'd divide the cost of making 10 by 10. If it was 5,000 things, take the cost of producing 5,000 of them and divide by 5,000. So that's why it's going to be the cost function divided by how many you produce, okay? Then there's something called the marginal cost. The marginal cost is the derivative of cost, the rate of change of cost, okay? And it gives the approximate cost, and this is where this becomes really useful, the approximate cost of producing one more item after X items have been produced. So it tells you the slope of the curve at any given point. So if it's at 400 and you've got a slope like this, it will tell you the rate of change right at 400. So in other words, it's going to tell you how much it costs to produce an item right around 400. So it'll tell you how much it costs to produce the 401st item. So that's the logic behind that. You know the rate of change for the cost, you know how much it costs right at that point, so you can predict how much the next one in line costs. Okay? Make sense? Okay. So let's look at an example and let's see if we can figure out how this explains volume discounts, okay, something called the economies of scale and stuff like that. So here's our function right here, and they purposefully made these very easy, okay? These are ridiculously oversimplified cost functions, okay? This is a linear function for crying out loud, okay? So the cost function is 500 plus 0.02x. It says find the average cost function, C bar, and find the marginal cost, C prime. So let's find C bar of x. C bar by definition is C of x divided by x. So that's going to be 500 plus 0.02x divided by x. If I rewrote that in a little bit easier fashion, C bar of x is going to be 500 over x plus 0.02. Got C bar. There's the average cost function. All the arithmetic look okay? All the algebra look all right? Okay, let's find C prime of x. Let's find the marginal cost function. The marginal cost function is just the derivative of cost. Derivative of 500 would be 0. Derivative of 0.02x would be 0.02. Okay, so average cost here, marginal cost right here. Okay, then it says determine the average and the marginal cost when x is equal to 1,000. Okay, what that means is figure out the average cost of producing 1,000 items. What is the average per item? And figure out the marginal cost of producing 1,000 items. So all we're doing here is if they gave me an x value of 1,000, my step here is just plug that into each one of them. Okay, so let's go ahead and do that. So I want to find C bar of 1,000. So that's going to be 500 over 1,000 plus 0.02, and I get 0.52. Okay, now if this is cost, we'll assume that that's dollars. Okay, so 52 cents is the average cost per item. If you make 1,000 of them and spread out the cost of over all 1,000 of them, they cost 52 cents a piece. Okay, what is C prime of 1,000 in this oversimplified example? 0.02. Okay? Okay. And it says, interpret the values obtained in part B. So say what these mean. And it's basically what I just said. This right here is the average cost for each of those 1,000 items. Okay? It's the cost spread over 1,000 items. And like they said right here, this is going to be marginal cost. Oops, let me keep my colors the same. This is marginal cost. So this is the cost of what? Okay, of making one more. Or in other words, that's how much it's going to cost to make the 1,001st item. That's pretty good. So after you make 1,000 of them, and in this simplified example, they're all 2 cents a piece, right? It wouldn't matter which one you made. Every one of them costs 2 cents, right? It is darn good. Okay? If every one of them costs 2 cents a piece, so this is where we've got to start thinking about this, and this is where we're getting to how can your answer in part C help explain the economies of scale and volume discounts? So have you ever walked into like all $1 or something like that, walk into a dollar store and look at something that they're selling for $1 and thought, how can they make any money on this? You know, some of the stuff you look at and think, I wouldn't pay 2 cents for this. Okay, but some of it you look at and you go, holy cow, that's a good deal. Or you go to Walmart and they've got something that's like 30% less than anybody else. You're thinking that's a great deal. Okay? So if every one of the items is 2 cents a piece, why is the average cost of the first 1,000, why is it 52 cents a piece? You have your fixed costs. Okay, so let's say we're making bicycles or widgets or whatever they are. Widgets are pretty classic. Okay, this means that it costs $500 for us just to open up our shop. Okay, so we're making bikes or widgets or whatever. Okay, it costs $500 just to open. Okay, in order to make one item, or we could even make it even worse, in order to make no items, we're really not very good at business. We're going to open a shop up and we're not going to make anything. It's going to cost us $500 to do that. If we make one item, it costs us 2 cents to make the item, but it costs us $500 to open it. So it costs us $500.02 to make one item. The average cost at that point is $500.02. If I make 2 of them, if I just make one more, it costs me $500.04. What's my average cost for making 2? $250.02. So just making 2 items, see how I've dropped my average cost way down? It continues to drop the more and more that I make until I'm at 1,000. It only costs me 52 cents a piece. Now, let's say you got an order from Walmart for 1,000 items, and you knew you could make them for 52 cents a piece. So you said, you know what? I'm not going to be too greedy on here. I'm going to sell it to them for $1. How much money are you making per item if you sell them for $1? 48 cents a piece. Okay? Now think about this. You've already covered your initial cost, all your setup cost, your fixed cost, your overhead, and it only cost you 2 cents a piece. So Walmart buys them for $1. You make 48 cents a piece. Okay? Let's say all $1 comes along and they say, hey, we'd like to buy some of those widgets, but we can't pay you $1 each. I got to pay you less than $1 so I can make some money, because I sell them for $1. 80 cents. I'll sell them to you for 80 cents. Okay? So the first 1,000 are 52 cents a piece. Okay? But if I mentally split it right there at 1,000, what if I sell them the next 1,000? How much does it cost me for every one of those next 1,000? 2 cents a piece. What if I'm selling them for 80 cents? I'm making 78 cents. Okay, now think about that. Think about why that makes sense in business. You sold them to Walmart for $1 a piece and you made 48 cents a piece. You're selling the next 1,000 for 20 cents less, but how much are you making per item? 78 cents. You're making more money even though you're selling it for less. In fact, you could drop your price down to, in this overly simplified example, you could drop your price down to 50 cents for all $1. And how much are you making at that point on those next 1,000? You're making 48 cents. The same that you were making when you sold them for $1. Okay. Now, you'd probably do something smart like split the difference and maybe say 80 cents, because then all $1 can buy them from you and still make money. And you're making a ton of money. You're rolling in it at that point. Okay. Does that make sense? Okay. All right.